Life is full of spectrums. Whether they're for visible light, coffee cup size, or spiciness of a pepper, we use them to express a range of options. Chemistry has its own set of spectrums, including one that ranges from acidic to basic. Chemists use the pH scale to analyze the properties of liquids to tell whether they are within the acidic, basic, or neutral ranges of the spectrum. pH defines the strength of an acid or a base and tells us what happens when they interact. We've talked about acid-base reactions here before, but today we'll use another term for them: neutralization reactions. They show up in everything from antacid tablets to water treatment facilities to household cleaning supplies. So today we'll talk about this subject in depth, as well as why it's important in environmental chemistry. Hi, I'm Will Komar, and welcome back to Study Hall Chemistry, presented by Arizona State University and Crash Course. Let's dive in. When we hear the word neutralization, the first thing that comes to mind for most of us probably isn't chemistry related at all. We probably heard the term in an action movie or a comic book talking about how a threat has been neutralized. Most of the time, it means the danger has been canceled out. The way we use neutralization in a chemistry setting actually isn't that far off from this. When we say something has been neutralized here in the lab, we mean that an acid-base reaction has taken place, and the products are no longer acids or bases. Instead, we get water and a salt. You'll probably recognize this from back when we talked about types of chemical reactions. In action movies and comic books, acids are basically villains. They eat through walls, they cause bad guy origin stories, and pose dangers to the public. Bases, especially strong ones, have the same reputation. Some cleaning products are bases that need to be handled with gloves so they don't damage our skin. But acids and bases actually have lots of cool properties that, when understood and handled safely, allow us to purify water, analyze pollutants, bake amazing loaves of bread, or even maintain the chlorine level in a swimming pool. To better understand neutralization, we can consult the pH scale, which defines the characteristics of all kinds of acids and bases, depending on how strong they are, from a scale of 0 to 14. Anything with a pH from 0 up to 7 we classify as an acid. Anything greater than 7 as a base, with 7 being neutral. To give this some context, let's plot some common substances we've talked about throughout this series along the scale. The pH numbers themselves aren't randomly assigned either. pH is the amount of hydrogen cations, or H+, in a substance. We'd call this amount its H+ concentration. If something has a high concentration of H+ ions, that means it's acidic. If it has a low concentration, it's alkaline or basic. Bases tend to have a higher concentration of OH- ions instead. It may sound counterintuitive, but acids have a high H+ concentration and a low pH value, while bases have a low H+ concentration and a high pH value. We calculate pH by using a negative logarithm of the concentration of H+, so we get this inverse relationship. But let's back up here. When we say H+, that's actually kind of a nickname. Like we talked about a while back, ionic or charged compounds dissociate in solution. Let's take neutral water as an example. Water dissociates to hydroxide and hydronium ions, where hydronium is H3O+. But for ease of use and familiarity, most chemists use hydronium and H+ interchangeably when we talk about pH. I'll keep calling hydronium by its nickname, H+, since we're friends. We hang out. Here's where neutralization comes in. When an acid and a base react together, their H+ and OH- ions combine to produce water and a salt. Let's break out the old ion vision glasses again to see this happen with a reaction between a strong acid, hydrochloric acid, and a strong base, sodium hydroxide. When in solution, hydrochloric acid dissociates into H+ cations and Cl- anions. The presence of H+ ions is how we can tell it's an acid. As for sodium hydroxide, we don't have any H+ ions, but we've got OH- anions hanging out in solution with our sodium cations, so we know it's a base. When we combine these together, the H+ and OH- ions can pair off. If all of them pair up, there won't be any acid or base ions left in the solution after the reaction. This means the pH is a neutral 7, so we can call the substance fully neutralized. Weak acids and bases only partially neutralize. We'll get into that next episode. In environmental science, pH can be an indicator of the health of an ecosystem, because when pollutants react with surface water or soil, the pH can slide up or down that scale. It moves away from neutrality to levels that can harm habitats or wildlife. We're actually seeing this happen right now with the acidification of Earth's oceans. To find out why, let's investigate with test tube. Normally, the ocean absorbs carbon dioxide from the air and produces some H+ ions and a base called bicarbonate. But combustion emissions and the greenhouse effect have led to a lot more carbon dioxide in the atmosphere. As a result, the oceans absorb more CO2, making the pH of the ocean, which normally sits at a basic pH of about 8.2, decrease to a more acidic pH of 8.1. While a drop this small might not seem like a big deal, this reaction actually has a domino effect on other reactions. That's because as the ocean gets more acidic, it forms more H+ ions and less bicarbonate. So, more acid and less base. To put this another way, the amount of ocean water itself doesn't change, but the amount of CO2 it's absorbing goes up. Since there can only be so much bicarbonate and H+, if we increase H+, the bicarbonate amount has to decrease. And if you remember, when we tried to find the number of atoms in a seashell, you know that shells are mostly made of calcium carbonate. Corals, oysters, mussels, and other marine life make those shells and skeletons through calcification, a process that relies on calcium and, bicarbonate. A more acidic pH means there's not enough bicarbonate to make shells, so we end up with a lot of shellless sea life that can't survive. And this, in turn, can throw off the dynamics of entire ecosystems. Chemistry helps us measure this threat, but now that we understand where the problem comes from, it could also help us neutralize it. Earlier, we described pH as the H+ concentration of a substance. And in general, concentration is the amount of a substance divided by its total volume. We can represent concentration as mass per volume, like grams per liter. And with a simple molar mass conversion, we can also represent it with molarity, or the amount of moles per liter. We use molarity to express the strength of any solution, not just acids and bases. But it's especially handy for neutralization because it'll tell us the strength of a solution using moles instead of pH, making it easier to do calculations with. Molarity also helps to find strong and weak acid-base relationships, which we'll get into next time. Today, for some shorthand, we'll write molarity with a capital M instead of writing out moles per liter. And when we write the molarity of a substance, we use brackets around the chemical formula like this. Since molarity is a kind of concentration, the terms are sometimes used interchangeably. When someone asks for the concentration, they usually mean molarity. As an example, let's say we want to find out the molarity of some cobalt-2 chloride, which can be used to make invisible ink. If our solution contains 48.4 grams of cobalt chloride and the volume is 0.743 liters, we could solve this in two steps. First, we convert our grams to moles by dividing by the molar mass of cobalt chloride, 129 grams per mole. And second, we divide moles by the volume. This gives us 0.505 as our molarity, or M, or moles per liter. Molarity is also helpful for labs ordering bulk chemicals for experiments. Solutions like hydrochloric acid are often sold as stock solutions with a standard concentration like 0.5 molar. It'd be convenient if the solution we need was always going to be 0.5, but not every reaction we do uses the same concentration. So instead of ordering every molarity we'd ever need, we're expected to dilute our stock solution to get the concentration that we want. This is kind of like buying concentrated frozen orange juice and watering it down until it tastes the way we like it. To solve problems where we need to dilute a stock solution to get the molarity we need, we use a molarity equation. It states that the initial volume times molarity is equal to the final volume times the final molarity. We use M1 and V1 for the initial molarity and volume, and M2 and V2 for the final ones. Let's say we have a stock solution of 0.5 molar of HCl, and we need 1 liter of HCl with a concentration of 0.1 molar. We can use the molarity equation to find out how much of the original stock we need to make that concentration. We're given 0.1 molar as our M2, 1 liter as our V2, and a stock concentration of 0.5 molar as our M1. That means we just need to solve for V1 in liters, so we should rearrange our equation. Now we just plug in our numbers and solve for our volume. Our molarity units will cancel, and we find out we need to add 0.2 liters of HCl stock solution to 0.8 liters of water to get the diluted concentration we need. Since we're working with a very strong acid, we need to dilute it by adding the acid to the water, not the other way around. If we don't start with the water in our flask, we could be dealing with an exothermic reaction. I wouldn't want to see that no matter what the molarity was. Molarity is a straightforward way for us to communicate the concentration and strength of a solution in terms of volume and moles. But there are also other terms for expressing concentration, including molality and normality. We don't have time to get into them here, but they're worth checking out on your own time. We won't always know the concentration of a solution we're supposed to analyze or use in a reaction, but we do have a tried and true method for finding it. That method is titration, a hands-on, acid-based neutralization approach that uses all the cool lab tools and some awesome color-changing liquid. Titration incrementally adds a substance with a known concentration to a sample of an unknown concentration that's had a small amount of color-changing pH indicator added to it. The rest is all math and stoichiometry, similar to how we calculated our volume of stock solution earlier. We'll walk through how to do an actual titration and calculation next time. Neutralization is a topic that pops up both in and out of the lab. It's important for protecting the environment, cleaning up chemical spills, and creating some of the household products we use every day. Acids and bases have a lot more to them than immediately meets the eye, so it's a good thing we've got a whole scale to define their properties. Next time, to celebrate our last episode, we'll continue the subject by talking about some strong acids and bases, defining buffers, and doing an awesome titration lab. See y'all there. Thanks for watching Study Hall Chemistry, which is produced by Arizona State University and the Crash Course team at Complexly. If you like this video and want to keep learning with us here in Study Hall, be sure to subscribe. You can learn more about ASU and the videos produced by Crash Course in the links in the description. See y'all next time.